I'm going to be talking to Dr. Simon Park, who is a professor of mechanical and manufacturing engineering at the University of Calgary. His team is one of 12 participants in the Carbon Fiber Grand Challenge that's being funded by Alberta Innovates and the Clean Resource Innovation Network. The idea is to take oil sands bitumen and find a way to turn it into cheap, plentiful carbon fiber that can be used in things like electric vehicles. So welcome to the interview, Simon.
Thank you, and it's a great pleasure to be here.
Well, I always enjoy talking to scientists about their work, and we'll get into the science in just a moment. But give me your take on whether your team and the other teams will be able to find a process that will be able to turn bitumen into carbon fiber.
I believe so. So one of the key importance of carbon fiber is how do you decrease the cost, and same time, how to reduce the greenhouse gas for making carbon fibers. And we do believe that this is possible by using oil sands and bitumen.
So my understanding is that that making carbon fiber now actually takes quite a bit of energy. Is that correct?
That's right. And it's like a baking process right now, turning some of the polymers into carbon.
And so your team's research, as I understand it, is you're going to be looking at chemical and electromagnetic treatments. Can you tell us a little bit about that?
Yes. So traditionally, you would put these spun fibers onto a furnace, and these furnace can take anywhere from several hours to more than tens of hours. And this requires a lot of energy. And what we are trying to do is how can we minimize this time by utilizing some other means? We are investigating two ways. First one is chemically, we can stabilize spun fibers. The second way is electromagnetic. The easy way to think about is using microwave technology. So it's like home microwave. When you put it in and you put the buttons, you can easily heat up your food quite quickly. And that's what we are trying to do. And there's a last process called graphitization, which requires really, really high temperature. And those cases we utilize a laser to make things really, really hot. And the benefit of our approach is that we can significantly reduce the time requires from spun fibers to carbon fibers.
And reducing time reduces costs, I would imagine.
That's right. So because of the processing, so it's important to understand that the costs associated with this actual feedstock price as well as the processing cost. And we do believe that by minimizing energy and time, we reduce costs, but at the same time, we can reduce greenhouse gas.
Right. And what are the results of your work in this area so far? Is it encouraging?
Yes, we have some promising results. Still, there are many obstacles that we have to overcome. And in terms of a processability of a bitumen or asphaltene, we do have to go through a lot of pre-processing and whatnot. And we are investigating what's the best way to pre-process so that we can process these materials easily.
Now, you say that there's a lot of work to be done, but the phase 2 of the challenge, which goes basically in 2022, is over at the end of this year, and phase 3 starts next year. Can you get all of that work done in such a short time?
Well, we are trying extremely hard. So in my team, we are working with researchers from University of Calgary. There's 2 other researchers, and also University of Alberta and Queen's University. So we are really collaborating hard to achieve the outcomes.
Yeah, it sounds like I've interviewed some of the other scientists who are working, and some of them with you, like Joanna Wong, and it sounds like there's a tremendous, regardless of who actually wins the challenge at the end of the day, all of this work will come together to support it. Each support the grand project, and the the industry and your researchers will be far ahead of where they were even a few years ago in terms of using, knowing how to use bitumen as a feedstock for making materials.
That's correct. That's correct. And in Alberta, we have a lot of bitumen, and from bitumen, there's a thing called asphaltene, and by utilizing these, I think we can make things more value added. And in terms of the technology, just from several years ago and now, we have gathered a lot of information and know-hows, and we are really looking forward to really from the research labs into the commercial hands.
Now, I understand I've interviewed the Alberta Innovates researchers, and they think that by the end of 2024, there will be at least one commercial process for making carbon fiber out of bitumen. But it sounds like there actually would be opportunities for materials other than carbon fiber. Is that fair to say?
So in terms of carbon fiber, there are two aspects. One is a long fibers, and the other one is the short fibers. So long fibers typically goes into airplanes and whatnot, and short fibers are filler materials that can be used in cement processes or other wooden products and other polymer products and whatnot. So different markets needs different type of things, and in terms of what we are trying to do, we are trying to look into both aspects, but there are lots of opportunities.
Is it fair to say that the University of Calgary is kind of becoming a research hub for this kind of work?
I believe so. So University of Calgary has been known for oil and gas, and a lot of researchers are transforming into something more environmentally friendly. And people are looking into, for example, for us, we are looking into carbon fibers from Alberta bitumen and Alberta oil sands.
Great. Is there anything you can tell us, Simon, maybe some of the challenges that you'll be having to deal with over the next year?
Yeah, so one of the big challenges that we face is that it's the feedstock. So right now we are heavily relying on the feedstock from sponsors, and the end result is based on what you begin with. And if we have a good feedstock to begin with, we believe that we have a good probability of achieving the goal. Same time, if we have a bad feedstock to begin with, it's a lot more challenging because it requires a lot more pre-processing needed to overcome those challenges.
What makes good feedstock versus bad feedstock?
So there are two aspects. One is processability. So you have to spun the fibers or making actual fibers. And so in terms of the rheological properties, and the second part is, can you make these things strong enough? Okay, because if you just carbonize it, they may not be strong enough because they often become very brittle. So we want to achieve these two through processing, pre-processing and other post-processing methods.
Now, I've talked to other economists and so on about bitumen, and not all bitumen is created equal. Some is a better resource than others. So the bitumen itself, what makes a good input, a good starting point for the kind of work that you're doing?
Yeah, so within the bitumen, there's a part called asphaltene, and this is the kind of bad stuff for use in fuels because it's a very carbon rich, okay, and less hydrogen. If you turn the ideas, because it has a high carbon contents, you can make better carbon fibers. What we see is that there's a lot more stuff in the process called the stabilization process, where you have oxygen deposition, so that you make things really, really strong. And we are investigating still, and that's what we are trying to achieve through some additional chemical processes.
So is it fair to say, Simon, that the bitumen that you use, if it has, you're probably looking for something with the fewest impurities that you can get and the highest carbon content that you can get? Would those be, say, two of the main criteria?
Yes, but at the same time, between these bitumen or asphaltene, there's a certain the structure that we are looking for. And we want to sort of optimize a different structures so that those are the chemical bonding structure is what makes things really strong at the end.
Oh, okay, so the chemical bonding structure. So can you tell us a little bit about that chemical bonding structure, what it looks like and what the optimal structure?
Yes. So in terms of the chemical bonding structure, what we are looking for is sort of the benzene ring type aromatic rings, okay? And those are what's making things really strong. And typically we start with regular, asphaltene or bitumen, and we have to, go through additional post-processing, whether it's chemical processing or oxidization process, so that we turn some of these into more aromatic rings so that we can exert the more strength.
Well, Simon, thank you very much for this. Really appreciate your insights.
Thank you, Markham. Appreciate it.